In this video, I'm going to go through how we name and write formulas for compounds, and it's going to cover material from parts of the first 6 sections of Chapter 3. Let's start out by going over what is a compound in the first place, and this picture is actually from the very first section of Chapter 1 of the textbook, and it shows different ways to classify matter. So matter can either be a pure substance or a mixture, and pure substances can be elements or compounds. Elements are the simplest unit of matter. We can't break them down any further. Compounds are units that consist of different elements chemically bonded together. And notice they are not mixtures of elements. They are compounds. In order to break up a compound into its elements, you'd have to do some sort of chemical reaction that would break the chemical bonds. Mixtures, on the other hand, are different substances, and they can often be separated by physical methods. It's important, first of all, when we're talking about compounds, to know what type of compound we're dealing with. As we're going to see, there are 2 main types of compounds, and the rules for naming them are a little bit different. So one type of compound is called an ionic compound. So in an ionic compound, the atoms are held together by ionic bonds, which are just the attractions between oppositely charged ions. So an ionic compound will have a cation, which is usually going to be a metal atom, and an anion, which is often a non-metal atom. But you can also have something called polyatomic ions. So polyatomic ions are ions that are actually more than one atom. So the entire unit has a charge. So for example, we can talk about the ammonium ion, which has the formula NH4+. So in the ammonium ion, you have 1 nitrogen and 4 hydrogen atoms, and then overall, you have a charge of +1. Now notice in formulas, right, we use subscripts to show the number of each atom in the formula. So there are 4 hydrogens, so I put a subscript of 4 after the hydrogen. There's only 1 nitrogen, so I didn't use any subscript. Now, ammonium is actually the only polyatomic cation we're going to come across in this class. There are a lot more polyatomic anions you should know, so I'll just do one example. Nitrate ion is NO3-. So you have 1 nitrogen and 3 oxygens with an overall negative charge. And there are many more polyatomic anions you should know that we will go over in class. The other type of compound has what's called covalent bonding, and so we call that a covalent compound. Now, covalent compounds often consist of molecules, so sometimes we refer to them as molecular compounds. So covalent compounds are when you have 2 non-metal atoms bonded together, right? If you only have non-metal atoms, neither atom wants to be a cation, so you're not going to have ionic bonding. So instead what happens is electrons get shared. And later in the semester, we'll talk in much more detail about how covalent bonding works. But for now, just understand it's the bonding between non-metal atoms. So we can write the formula for molecular compounds. We call that the molecular formula. That just shows how many of each atom there are in the molecule. And I already mentioned this, but again, we use subscripts in the formula. So a molecule that everyone knows, of course, is H2O, right? Water. All water molecules contain exactly 2 hydrogen atoms and 1 oxygen atom. So let's start out by talking about how we name covalent or molecular compounds. This is section 2. I'm going over those first because the rules for naming covalent compounds is a little bit easier, so we'll do that one first. And we're just going to focus on what we call binary covalent compounds, which is just a covalent compound between 2 elements. And of course, they're going to be non-metal elements. So first of all, you have to decide which element is going to go first in the name and which will be second. And that's not always obvious, but the general rule is the element that's closer to being a metal will come first. So that means the element further to the left or maybe further down in the periodic table comes first. And then the second element, we change the ending of its name to IDE. So for example, chlorine ends in INE becomes IDE. So chlorine becomes chloride. Oxygen, when it's the second element in the name, becomes oxide, and so on. And as we'll see, these are just like the names when these elements are anions. And then in order to show the number of each element in the formula, we use prefixes that we call Greek prefixes And here they are. So this is taken from table 3.1 in the textbook. So when you have one of an element, that's mono. 2 is di, and 3 is tri, 4 is tetra. And then the remaining ones, you probably come across these before in geometry when you talk about the number of sides to a shape. Of course, a 5-sided shape is a pentagon. So penta is the prefix we use in chemistry when there's 5 of something, and then we have hexa and hepta and octa and so on. So you should know the prefixes up to 10. So here's some flowcharts from the textbook which show how we name the compounds. So you start again with the first element in the name with a prefix if necessary, and then the second element and give it an IDE ending. So on the right you can see an example of the compound N2O. So the elements there are nitrogen and oxygen. We put nitrogen first. There's 2 nitrogens, so we use the prefix di in front of the nitrogen, and then there's 1 oxygen, so we use the prefix mono. So you cannot just say dinitrogen oxide because that doesn't tell you how many oxygens there are. So we use the mono formula, and actually monooxide becomes monoxide. So in total, the name is dinitrogen monoxide. So you always want to put a prefix on the second element, even if there's only one of that element, use the mono prefix, but we don't put mono on the first element. So we can do a few more examples. CO2, okay, everyone's familiar with that compound. That, of course, is carbon dioxide. So now you can see where that name comes from. There's 1 carbon in the formula. We don't put the prefix mono on the first element, but we do need a prefix on the second element. And the prefix for 2 is di, so that's carbon dioxide. And we have to say dioxide because there's another oxide of carbon with just 1 oxygen, so that would be carbon monoxide. Again, it's monooxide. We drop one of the O's there, just make it mon oxide. And then we can do P2O5. Now there's more than one of the first element, so we use a prefix. So P is phosphorus, so it's diphosphorus. And then there's 5 oxygens. The prefix for 5 is penta. But again, you lose the last letter of the prefix with oxide, so it just becomes pentoxide. 2 phosphoruses and 5 oxygens. There are a few common names that you should know. Of course, we already mentioned H2O is water. CH4, that's known as methane, and NH3 is known as ammonia. So those are very commonly used. So you should know those names. So now moving on to section 3 of the textbook, we can talk about how we write the formulas for ionic compounds. And when we write a formula of an ionic compound, what we're really saying is we're specifying the contents of the formula unit of that compound. So the formula unit is just the simplest whole number ratio of the different ions in the compound. And what's important is the formula unit must be neutral. It cannot have a charge. So you can never have a substance that has an overall positive or negative charge. So the charge of all the cations must balance out the charge of all the anions. So we have to put subscripts then in the formula so that the charges balance. For example, what about a compound between sodium and chlorine? Sodium has a +1 charge, so it's Na+. Chloride is -1. So when you have a +1 and a -1, you only need one of each ion to balance charges out, so it's just NaCl. Now you could also have magnesium is 2+, oxide is 2-. So again, if you have a +2 and a -2, if the positive charge of the cation is the same as the negative charge of the anion, you just need one of each to balance out. So that's just MgO. On the other hand, if you had magnesium and chlorine, then in this case, you would need 2 -1s to balance out the +2. So we need 2 of those. So the formula is MgCl2. Now let's say you had potassium, which is +1, and sulfur, sulfide is -2. Now in this case, you need 2 +1s to balance out the sulfide, the -2, so we would say K2S. Do one more example. Aluminum oxide. Aluminum is +3, and oxide, as we already seen, is -2. So there's a trick that we can do here in this case. What you can do is you can take the charge of one ion and move it over and make that the subscript of the other ion. and vice versa. So what we get is Al2O3. Sometimes you may have to simplify the numbers to get smaller whole numbers. We don't have to in this case. And so we can check that this is neutral. If you have two aluminums, that's 2 plus 3s is plus 6. Then you have 3 minus 2s is minus 6, so plus 6 balances out minus 6. Now, how did I know the charges of these different elements? Well, you can see from this table, it's figure 3.7 in the textbook. Some elements always have the same charge. In particular, the main group elements will often gain or lose electrons so that they have the same number of electrons as one of the noble gases. So remember, the noble gas is this group. So for example, the alkali metals, a group 1A element, they only need to lose 1 electron to have the same number of electrons as a noble gas. So for example, sodium has 11 electrons. If it loses 1 electron, becomes plus 1, it's going to have 10 electrons just like neon. So the group 1A elements are plus 1, the group 2A elements are plus 2, aluminum in group 3A is plus 3. And then you can see for anions, halogens need to gain 1 electron to have the same number of electrons as a noble gas. So they're minus 1, oxide and sulfide are minus 2. The transition metals are a little bit more complicated, and in some cases, as you can see on this chart, they can have more than one charge. They don't always have the same charge. Let's look at some formulas involving polyatomic ions. So what about, how would we write the formula of sodium nitrate? So sodium, as we've already seen, is plus 1, and then nitrate is minus 1. So again, just like with sodium chloride, you just need 1 cation and 1 anion. So it's NaNO3. Potassium carbonate, potassium is K+, it's plus 1. Carbonate, this is one that you just have to memorize, it's CO3 2 minus. So we need 2 plus 1s to balance out the CO3 2 minus. So it's K2CO3. Now what about zinc nitrate? Zinc, turns out, is plus 2. Nitrate is minus 1. So we need 2 nitrates to balance out the zinc. When you have more than one of a polyatomic ion, you have to put the polyatomic ion in parentheses. So we put the nitrate in parentheses, and then we put the 2 outside the parentheses to show that there are 2 of them. So remember that when you have a subscript just by itself, it only applies to the atom that comes directly before it. When you put a subscript outside the parentheses, then it applies to everything inside the parentheses. So you're multiplying the whole NO3 unit by 2. Okay, so now we can do the reverse, right? How would you name an ionic compound given its formula? And there's actually 2 different methods we use, and it depends on the cation of the formula. If the cation always has the same charge, then it's quite simple. You just write the name of the cation and then the name of the anion. Now keep in mind that monoatomic anions will often have the IDE ending, like chloride and oxide and things like that. Polyatomic ions, as you learn their names, you'll notice that they tend to end in ATE or ITE. Now the second method is for the cations that can have more than one charge. In that case, what we do is you have to specify the charge of the cation by writing its charge after it with Roman numerals. Now keep in mind, this is an important point, we do not use the prefixes that we saw already. We don't use those in ionic compounds, only in covalent compounds. Okay, so here's another picture from the textbook going over charges of ions. So the ions there that sort of in that orangey color, you can see that those are the ones that always have the same charge. So we don't use Roman numerals in names of their compounds. That's the group 1A, 2A, and aluminum. And then these 3 you just need to memorize. Zinc and cadmium are always plus 2, and silver is always plus 1. So when the cation is one of these, we don't need to use a Roman numeral. The rest, so most of the rest of the transition metals, as well as tin and lead, which are here in the periodic table, they can have more than one charge, so we have to specify the charge with Roman numerals. And again, here's some flowcharts from the textbook illustrating how we name ionic compounds. So you can see CaCl2, that's a compound of calcium and chloride. Calcium's in group 2A, so it's always plus 2, so we don't use a Roman numeral. So it's just calcium chloride, just the name of the cation, the name of the anion. Iron, though, is a transition metal that can have more than one charge. Now, if you remember that sulfate is SO4 2 minus, and you can see from the formula that there's 1 iron per 1 sulfate. If the anion is -2, then the cation must be +2. So we put that charge as a Roman numeral. So this compound is iron 2 sulfate. Okay, let me do a few more examples. So iron makes 2 compounds with chlorine, FeCl2, and FeCl3. Now we can't just say iron chloride because that wouldn't tell you which of these compounds it is. So again, we use the Roman numerals. So this first one is iron 2 chloride because the iron is +2 there, and then the second one, the iron is +3, so it's iron 3 in Roman numerals, chloride. And then in a similar way, tin can be +2 or +4, so SnCl2 is tin 2 chloride, and SnCl4 is tin Roman numeral chloride. Now, one thing that you should be aware of is that the Roman numeral, now remember, that is the charge of the cation. It doesn't necessarily correspond to one of the subscripts in the formulas. So, for example, PbO2, Pb is lead. This is lead 4 oxide. Now, there's no 4 anywhere in the formula, but there is a 4 in the name. And that's because oxide, remember, is 2 minus. So if you have 2 oxides, that's 2 minus 2's, the cation must therefore be +4. So this is lead 4 oxide, not lead 2 oxide. That would be just PbO. So section 6 from the textbook goes through a summary of all the rules of naming, and it leads to this very complicated flowchart, as you can see there. It's actually more complicated because it includes some naming of acids, which I didn't want to go over in this lecture because I don't want to make it too long, but we can talk about those briefly in class. But just as a summary, then we saw that in binary covalent compounds, which are a compound between 2 non-metal atoms, we use the Greek prefixes in the naming. For ionic compounds, which consist of a cation, which is either going to be a metal atom or the one polyatomic cation you need to know, ammonium, NH4+, and then a monoatomic non-metal anion or a polyatomic anion. Those are ionic compounds, and then if necessary, we use the Roman numerals in their name if the cation can have more than one charge. So just to finish off, I'll do 3 more examples. Now these compounds look pretty similar. In each case, we have an element bonded to 2 chlorine atoms, SCl2, so S is sulfur. Sulfur and chlorine are both non-metal atoms, so this is a covalent compound, so it's sulfur dichloride. We use the prefixes there. MgCl2 is magnesium chloride, and we don't put a 2 after the magnesium, even though the magnesium is +2. Magnesium's always +2, so we don't use the Roman numeral, and it's not magnesium dichloride. That's a common mistake students will make. It's not dichloride because we only use the prefixes on covalent compounds. This is an ionic compound. CuCl2 is also an ionic compound. Cu is copper. Copper is another transition metal that can have more than one charge, and we can see here that if we have 2 minus 1s, 2 chlorides, the copper must therefore be +2. So this is copper 2 chloride. Again, don't use prefixes, not copper dichloride. Never use prefixes on ionic compounds, but instead we use the Roman numeral to show that the copper has a +2 charge. Okay, so that was some examples of how we name compounds and write formulas, and we'll practice a lot more in class. So thanks for listening, and I'm going to stop there.